Now let's see if we can actually calculate the numeric number for the entropy change. Okay, so let's look at this reaction. I got ammonia plus carbon dioxide forming urea and water. The calculation is very similar to what we did with delta H, okay, with your ether formations, except now we're using entropy terms. Now, we can go ahead, in this particular case, make a prediction of what delta S is going to be. I'm going from gaseous molecules to aqueous and liquids. I'm going from 3 molecules to 2 molecules. So what I'm doing is going from a case of having a highly disordered system to a less disordered system. So that's a case of having a delta S being negative. So we're predicting here that we should get a negative delta S. Now we're going to actually calculate this and see if that's what we get. So you have to look in the table for your entropies. Okay, I got 193 joules per mole Kelvin for ammonia, 214 for carbon dioxide, 174 for urea, and 70 for water liquid. Okay, so I have to look those up in the table, or they be given to me in a problem. Now we're going to use the law of summations, which means I have my summation of my entropies of my products, number of moles taken account, minus the summation of my entropy of my reactants, accounting for the number of moles. Plug in my values. I get 1 mole of urea times my 174 joules per mole Kelvin. My moles cancel. Okay. Add that to my water, which is 1 mole of water times my 70 joules per mole Kelvin of my water. My moles cancel. Okay. I add those up. Those are my product terms. Okay. So that's my products. Then I'm going to subtract my reactants terms, okay, which in this case I have 2 moles of ammonia times its entropy, which is 193 joules per mole Kelvin, where's my moles cancel, and I have 1 mole of carbon dioxide times its entropy, which is 214 joules per mole Kelvin, my moles cancel. So I have my products minus my reactants, and overall I get a negative 356 joules per Kelvin, which is what we predicted, right? We said that we saw there's going to be a decrease in disorder in the system, so we expected this to be a negative value, and it is. Okay, decrease in disorder as predicted. Now, if I'm just going to solely look at the the entropy of this, based that it's a negative number, we would say that this is going to end up being a non-spontaneous reaction because of that. Okay. However, the enthalpy may be enough to switch it to be a spontaneous reaction. Now, the question arises as to how do we decide if enthalpy or entropy dictates the spontaneity of a reaction? What is the relationship between delta H and delta S? Okay, if I have one predicting spontaneous and one predicting non-spontaneous, how am I going to determine which one's going to win and dictate the overall spontaneity of the reaction? Well, we will look at something that was developed by American physicist J. Willard Gibbs, who introduced the concept of free energy, sometimes referred to as Gibbs free energy, and is given the symbol capital G, which is the thermodynamic quantity defined by the following equation. Delta G is equal to delta H minus T delta S. So if we can calculate the enthalpy term, and we can calculate the entropy term, and we put this into this equation, we get some value for G. By looking at that value of G, we can determine whether it's a spontaneous or non-spontaneous reaction. In this equation, T has to be on the Kelvin scale, which is a value that's always positive. It's 0 or higher. There's no negative temperature on the Kelvin scale. So this quantity gives us a direct criterion for spontaneity of reaction. By the value of delta G will just dictate to us whether it's a spontaneous or non-spontaneous reaction by accounting for that enthalpy and that entropy term in that equation. Changes in your enthalpy and entropy during a reaction result in a change in that Gibbs free energy. Okay, by that following equation, delta G is equal to delta H minus T delta S. At a given temperature and pressure, if we find delta G is equal to 0, what that is telling us is that the reaction is at equilibrium, okay, and has significant amounts of both reactants and products. The significance of delta G equals 0 is that the temperature at that point where delta G is equal to 0, okay, is that transfer point where the reaction switches from spontaneous to non-spontaneous. If it was spontaneous all the way to a certain temperature, when I get to that temperature, that delta G is equal to 0, then it's going to flip to the other one, okay, where the entropy will now be ruling, and we go from that point. Okay, so that delta G equals 0 is that switch point. If the reaction was non-spontaneous, from that point on it would be spontaneous, okay, or vice versa. If delta G is greater than 0, the reaction is non-spontaneous as written, and the reactants do not give significant amounts of products at equilibrium. So it doesn't go very far before it reaches equilibrium. So it doesn't make a lot of products, okay? So what we're saying here is if I have a positive delta G, it's a non-spontaneous reaction. If I have a positive delta G, I have a non-spontaneous reaction. If delta G is less than 0, the reaction is spontaneous as written, and the reactions transfer almost entirely to products when equilibrium is reached. So the reactions go far to the right and form a lot of products. So in other words here, if I'm looking at a negative delta G, then I'm looking at a spontaneous reaction. Okay, a spontaneous reaction. So by doing the calculation of Gibbs free energy, we can look at the sign of that delta G and decide if we're looking at a spontaneous or non-spontaneous reaction. If we had delta G is equal to 0, we're looking at that point where the reaction could switch from spontaneous to non-spontaneous or vice versa. Let's look at the relationship among the signs of delta H, delta S, and delta G and spontaneity. Okay, I want you to realize that temperature will dictate, but note that the temperature will dictate which one we rule. Okay, we compare in delta H and delta S, and basically that temperature is going to dictate which one's going to be bigger. Okay, also realize that temperature is in Kelvin, therefore there's no negative temperatures. Let's start off with the easy ones first, where there's no competition. Okay, if I talk about an exothermic reaction, that favors a spontaneous reaction. If I talk about an increase in disorder, that favors a spontaneous reaction. So therefore, there's no competition between the two. Since both of them are favoring a spontaneous reaction, then the overall reaction must be spontaneous. Mathematically, this works out. I got a negative delta H. I got a positive delta S. Well, a negative times a positive gives me a negative. So a negative and a negative, the whole thing's a negative, okay, which by our definition is a spontaneous reaction. So at all temperatures, okay, at all temperatures, we have a spontaneous reaction. There's no competition between the species, between those components, okay. They both favor a spontaneous reaction. Let's look at this case. Okay, I got an endothermic reaction, which favors a non-spontaneous reaction. A decrease in disorder, which favors a non-spontaneous reaction. Well, since they both favor a non-spontaneous reaction, once again, no competition. The whole thing's going to be a non-spontaneous reaction. Mathematically, we have a positive delta H. I have a negative delta S. A negative times a negative gives me a positive, which gives the whole thing a positive value. So once again, it's going to be non-spontaneous at all temperatures. Doesn't matter what the temperature is, they both are favoring a non-spontaneous reaction. Well, here's the first one. We're going to talk about competition. Okay, I have an exothermic reaction, which favors a spontaneous reaction. I have a decrease in disorder, which favors a non-spontaneous reaction. So you can see now I have opposites. So it could be positive or it could be negative for delta G. How are we going to determine it? Well, that's where temperature becomes very important. For at low temperatures, when I'm meaning room temperature, 25 degrees C, 298 Kelvin, 300 Kelvin, 400 Kelvin, very low temperatures, what's going to happen is your delta H is going to be larger than your T delta S. Okay, that value is going to be larger. So in that case, we go back to what delta H is. Delta H is favoring a spontaneous reaction. Therefore, since delta H is a spontaneous reaction, I'm going to end up with a negative delta G, which is favoring a spontaneous reaction. At high temperatures, okay, we're talking 1,000, 1,500 K, very large temperatures, what's going to happen is the T delta S is going to be larger than the delta H. So then my entropy term is going to dictate the overall process. Well, since it's favoring a non-spontaneous reaction, we're going to end up with a positive delta G, which means the overall process is going to be non-spontaneous. Let's look at this case. I have an endothermic process that favors a non-spontaneous reaction. I have an increase in disorder which favors a spontaneous reaction. So once again, I have a conflict, okay? So it could be positive and negative. Once again, temperature is going to dictate it. If we talk about low temperatures, then we're going to say that delta H is larger than T delta S. Therefore, my endothermic process is going to dictate it, which means that I'm going to have a positive delta G, and it's going to be a non-spontaneous reaction at low temperatures. If I'm at high temperatures, what's going to happen is my T delta S is going to be larger than my delta H, which means my disorder is going to dictate my process, which is favoring a spontaneous reaction. Therefore, I'm going to get a negative delta G, and we're going to have a spontaneous reaction. Bottom line, okay, what we're talking about here is that enthalpy is going to rule at low temperature, okay, and entropy is going to rule at high temperature. Okay, so if we have a conflict between the two at low temperatures, whatever enthalpy, it's going to rule the overall spontaneity of the equation. If you're at high temperatures, then entropy is going to rule the overall spontaneity of the equation. The standard free energy change, delta G superscript naught there, okay, standard. That's why we got that superscript 0, basically talking about 25 degrees C, 1 atmosphere, 1 molarity, is the free energy change that occurs when reactants and products are in their standard states. The next example illustrates the calculation of the standard free energy delta G naught from delta H and delta S. Basically what we can do here is I want to calculate my delta G, a numeric value for it. I can figure out my delta H's and my delta S by using the law of summations. Okay, so I can figure out my delta HF doing my summations of my delta HF minus my delta of my products minus my delta HFs of my reactants, and I can do the same thing with my delta S. I can find that by doing my summations of my entropies of my products minus my entropies of my reactants. Plug that into my equation, come up with a numeric value for delta G, and then decide if I got a spontaneous or non-spontaneous reaction. What is the standard free energy change, the delta G naught, for the following reaction at 25 degrees C? I have N2 plus 3H2 gives me 2 ammonias. I can look in the tables and find out the values of delta HFs and my entropies. Now, when I look in the tables, should I be able to find N2 and H2 in the tables for my delta HFs? The answer is no, because those are the elementary species, okay? And we said that it's a relative scale. Now, if I look in the tables for my entropies, will I find a numeric value for N2 and H2? The answer is yes, because that's an absolute scale. So I'll look in the tables and I find some values. I get 0 for nitrogen, 0 for hydrogen, and a negative 45.9 for ammonia, and 191.5 for nitrogen and 130.6 for hydrogen for my entropy, and 193 joules per mole Kelvin my entropy of my ammonia. Now, since this is a simple calculation for the delta HF, we can make a prediction of what's going to happen here because I have products but I have no reactants. That's 0. So I know then that the overall delta HF, overall delta H of this reaction is going to be a negative value. Since my enthalpy is a negative, that means it's an exothermic reaction. That means it favors a spontaneous reaction. For the entropy, we're going from 4 moles of gas to 2 moles of gas. So that's a decrease in disorder. So we expect that to be a negative delta S, which favors a non-spontaneous reaction. So we can predict that we're going to see a negative delta H in this spontaneous reaction and a negative delta S, which is a non-spontaneous. So we have contradiction here. One of them's going to have to win. So how are we going to decide which one's going to win in this calculation? Well, it goes back to temperature, right? Our temperature is at 25 degrees C. That's considered low temperature. At low temperature, is delta H or delta S going to rule? Well, it'll be delta H. So we're saying that that's going to dictate our overall process. So since delta H is a negative in favoring a spontaneous reaction, then we predict that delta G then will be a negative value. So we can do our calculation and see if we come up with that conclusion. The reason we're able to do this one so easily is because of the delta H was 0 for the reactant. So if they had numbers there, then it would be a little bit harder to do in your head. But since we could do it, I went ahead and did it. So we're basically predicting that we're going to get a negative delta G, a spontaneous reaction out of this process. So you take your reaction. You now do your law of summations. We do it for our delta HF, products minus reactants. I get 2 moles of my ammonia, time my negative 45.9 kilojoules per mole of ammonia, so my moles cancel. That's my products. Okay. And I'm going to subtract my amount of reactants, which in this case was all 0. So it gives me a negative 91.8 kilojoules, which is an exothermic process. Okay. And we favors a spontaneous reaction. Entropy, products minus reactants. I get 2 moles of ammonia. That cancels with my moles, well, 193 joules per mole Kelvin. That is my products. Okay, I'm going to subtract my reactants, which is 1 mole of nitrogen, time 191.5 joules per mole Kelvin, moles cancel, plus my 3 moles of hydrogen, moles cancel, with moles, 130.6 joules per mole Kelvin. Add those numbers up, and I get a negative 197 joules per Kelvin, which is basically our decrease in my entropy, which is what we predicted. Okay, that favors a non-spontaneous reaction. Okay, which is what we said we were going to get. Now notice I went from 197 joules per Kelvin to a negative 0.197 kilojoules per mole. Basically, I divided by 1,000 and changed from joules to kilojoules. Why did I do that? Well, when I plug it in my delta G equation, I need to subtract apples and apples. So I need to subtract kilojoules from kilojoules, or joules from joules. So I chose to do kilojoules. Okay, so I did that little conversion before I can plug that into my equation. I have to have the same unit to be able to subtract values. So for this point, I'll plug it into my equation, okay, which is delta G is equal to delta H minus T delta S. So I'll plug in delta H, which is a negative 91.8 kilojoules. I plug in my temperature, which is 25 degrees C. I can convert it to Kelvin, which is 298 Kelvin, and multiply that by delta S, which we said is a negative 0.197 kilojoules per Kelvin. Okay, Kelvins cancel. Now I have kilojoules minus kilojoules, which I can do. Okay, so I get a negative 91.8 minus a minus, which means a plus. 298 times 0.197. I get my value, which is a negative 33.1 kilojoules, which is what we predicted. We said it would be a negative value because we said it would be a spontaneous reaction as written. Okay, and that was being dictated. Okay, that was being dictated, we said, because of that negative 91.8 in its enthalpy. So at low temperature, the enthalpy was going to rule, and it did in this case. If we were at a higher temperature, 1,000 or so, then what would happen is the entropy would rule, and it would be the opposite. It would be a non-spontaneous reaction. The standard free energy of formation, the delta GF of a substance, is the free energy change that occurs when 1 mole of a substance is formed from its elements in their stable states at 1 atmosphere pressure and 25 degrees C. This definition is written exactly the same as delta HF. Okay, once again, this is a delta, Okay, so we're talking about a relative term here. So what do you think is going to happen when I talk about oxygen, O2 gas at room temperature? What kind of delta G do you expect? 0, just like we did with delta HF. Entropy was not the case. It was some numeric value because that was an absolute scale. Well, this is a relative scale. By tabulating delta GFs for substances, we can calculate the delta G of reaction using the law of summations, just like we did with delta H's and also with entropies. Summations of your delta GFs products minus that of your reactants. So we can calculate delta G using delta H and S data, or we can go ahead and calculate delta G directly from delta GF data. Example, calculate delta G using the standard free energies of formation. Okay, so we're talking about ethanol plus oxygen gives me carbon dioxide and water. So I'll go look in the tables for delta GFs. I find it for ethanol, I find it for CO2, I find it for water gas, but I don't find it for oxygen gas. Why? Because it's a relative scale, so it's a 0 value. So I get a negative 174.8 kilojoules per mole for ethanol, 0 for oxygen, a negative 394.4 for carbon dioxide, and a negative 228.6 kilojoules per mole for water gas. My summations of products minus reactants, plug in my values. I get, for my products, okay, I subtract my products first. I got 2 moles of carbon dioxide times my negative 394.4 kilojoules per mole, therefore my moles cancel. And I got 3 moles of water times my negative 228.6 kilojoules per mole, my moles of water cancels. Okay, so that gives me my numeric value for my products. Then I have to subtract my reactants. I have 1 mole of my ethanol times my negative 174.8 kilojoules per mole. So my moles cancel. And I got to add that to 3 moles of oxygen times 0, which is 0. And mathematically, I get a value of a negative 1,299.8 kilojoules. Since it's a negative value, is this a spontaneous or non-spontaneous reaction? It's a spontaneous reaction. The free energy change when reactants are in non-standard states, meaning other than 298 Kelvin, 1 atmosphere, or 1 molarity, okay, is related to the standard free energy change, delta G, by the following equation. Your delta G, meaning your non-standard, okay, this is your non-standard delta G, is equal to your standard delta G plus RT natural log of Q. So in essence, it's equivalent with this correcting factor of RT natural log of Q. So your non-standard equals your standard plus this correcting factor of RT natural log of Q. Now what are those values? Well, Q is your thermodynamic form of the reaction quotient, meaning your products over reactants. It's not necessarily equilibrium, so we call it Q. It could be any initial values, okay, so we call it Q. T is your temperature in Kelvin, and R is your ideal gas constant, but it has to be a particular one in the sense of units to cancel out. So we're going to use R is equal to 8.31 joules per mole Kelvin. So this in essence can give us the calculation of a non-standard reaction, give us our value comparison to that standard one with this correcting factor. Now, delta G represents an instantaneous change in free energy at some point of the reaction approaching that equilibrium, meaning delta G equals 0. Some point before we reach equilibrium, the reaction is working toward getting there. Okay, so let's talk about equilibrium now. If I'm at equilibrium, meaning delta G is equal to 0, then that Q also is going to change because it's not Q anymore. I'm at equilibrium, that's K. So in essence, I can take this whole reaction and rewrite it and come up with a new reaction which has a relationship between K and delta G. So I can take this reaction at equilibrium and say then, okay, if I'm at equilibrium, then I know that delta G is equal to 0, okay? And I also know that Q then is equal to K. So I get 0 is equal to delta G naught plus RT natural log of K. Rearranging this, I now get delta G is equal to a negative RT natural log of K. So what I have is another equation that I can determine K from delta G, or if I have delta G, I can figure K, or for whatever the case may be. Okay, another relationship. And these are related, and they're also complementary to each other. You may recall we talked about the size of K. When K is greater than 1, that means their equilibrium lies to the right. It means it's a spontaneous reaction. Okay, spontaneous reaction as written. Okay, well, mathematically, if I take the natural log of K being greater than 1, I'm going to get some positive value here. Well, negative or positive means a negative delta G, which is the same thing as saying a spontaneous reaction. Okay. If K is less than 1, okay, K is less than 1, meaning the equilibrium lies to the left, that means we're not going to make a lot of products. Basically, we're talking about a non-spontaneous reaction. Okay. Well, mathematically, if K is less than 1, I'm going to take the natural log of it. It's going to be a negative value. If I got a negative times a negative, I'm going to end up with a positive delta G, which is an indication of a non-spontaneous reaction. So what happens is this equation is complementary. This K and delta G are both working together to either say that we have a spontaneous or a non-spontaneous reaction. So we can use this equation to solve for K if we want, which we're going to look at in the next example. Find the value of the equilibrium constant K at 25 degrees C for the following reaction. The standard free energy change, delta G, is equal to a negative 13.6 kilojoules per mole. So what we're doing here is we're trying to figure out K by using delta G. Now, this problem could be a lot more entailed than what I have written right here. I gave you delta G directly, but you got to realize it is possible that we have to figure out delta G naught from delta H minus T delta S. So you would have to do your law of summations to figure out delta H, do your law of summations to figure out your delta S, plug it into this equation, then solve for delta G, then do what we're about to do in this calculation. But to simplify things, since we already calculated delta H and delta S several times, I decided to just go ahead and give you delta G directly in this problem and just handle this new concept. So we can rearrange our delta G equal to a negative RT natural log of K, rearrange it. We're trying to solve for K. Okay, so I'll go ahead and divide through by negative RT. So I get natural log of K is equal to delta G naught divided by negative RT. Substituting in my values, I got a negative 13.6 times 10 to the third joules per mole for my delta G. Notice that it was given to me in kilojoules, but I converted it to joules by doing that 10 to the third because I want my units to cancel. Okay, so I had to change that. Divided by R, which is 8.31 joules per mole Kelvin. And divided by my temperature, what has to be in Kelvin, which is 298 Kelvin. Now I'm trying to solve for K. What are the units on K? You may recall they are unitless. There are no units. So I need all these units to cancel. One of the reasons why I had to convert from kilojoules to joules. All the units should cancel out, and they do. There's nothing left. It's unitless. Now how do we handle the natural log of K equal to 5.49? Well, what we did was we talked about in the past. I got to do the anti-natural log. Okay, the anti-natural log, which is saying doing e to the x. Okay, I got to do the e to the x. So therefore, I'll take the anti-log of both sides, which means K then is equal to e to the 5.49. On your calculator, there's a button or a table where you can look up e to the x, which gives me 2.42 times 10 to the second, which is equal to 240. Remember, we said if K is greater than 1, which it is in this case, that's favoring a spontaneous reaction. And we also have a negative delta G, which favors a spontaneous reaction. So they're complementary to each other. Both of them are saying that we have a spontaneous reaction. Now, we typically assume that delta H naught and delta S naught are essentially constant with respect to temperature, meaning if we change the temperature, those values don't change that much. We don't have tables of all the different temperatures, all the different delta H's and delta S's. We tend to use the 25-degree data to make calculations. You get the value of delta G subscript T at naught at any temperature T by substituting the values of delta H naught and delta S naught at 25 degrees into our equation. It is the same Gibbs free energy equation, except the one difference is that I have a subscript T here that basically tells me what the temperature is we're talking about. So you can get a delta G naught at 25 degrees C, which is what we've just been doing, or you could do a delta G naught at, say, 100 degrees C, which is telling you I'm using the 25 degree data, but I'm doing it at a different temperature. Okay, I'm not doing it at 25 degrees C. Same equation, but we've got to write that subscript to tell us what temperature we're using that 25 degree data at. Let's look at an example. Find the delta G for the following reactions at 25 degree and 1000 degrees, so we're doing two different calculations, and relate this to the reaction of spontaneity. So we're looking at calcium carbonate breaking up into calcium oxide and carbon dioxide. So I want to calculate delta G, so we'll use Gibbs free energy, so we have to calculate delta H's and delta S's. So look in the tables and find these values. Delta HF's negative 1206.9 and negative 635.1 and negative 393.5 kilojoules per mole. My entropy is 92.9, 38.2, 213.7 joules per mole Kelvin. Now I'll take these values and plug them in, do my law of summations. So for my delta HF, law of summations of products minus reactants, I get negative 635.1. Now realize that these are all 1-to-1 moles, so it's understood that I have 1 mole in here. I didn't write it for each one. They cancel out, okay, so I didn't bother to do the 1 mole. So I got my 1 mole of my calcium oxide times my negative 635.1 kilojoules per mole of calcium oxide. Moles cancel. Add my carbon dioxide, which is 1 mole of carbon dioxide. Okay, time it's negative 393.5 kilojoules per mole. Moles cancel. Then I have my 1 mole of calcium carbonate times my negative 1206.9 kilojoules per mole. Do the math, I end up with 178.3 kilojoules. That's an endothermic process, and it favors a non-spontaneous reaction. Okay, do the same thing with entropy, products minus reactants. Once again, we're accounting for our moles. I got 1 mole of my calcium oxide times its entropy, 38.2 kilojoules, joules per mole Kelvin, plus my carbon dioxide, 1 mole of my carbon dioxide times my entropy, which is 213.7 joules per mole Kelvin. So my moles cancel. Okay. Minus that of my reactants. In this case, I got 1 mole of calcium carbonate times my 92.9 joules per mole Kelvin. So my moles calcium carbonate cancels out. Add that up. I come up with 159.0 joules per Kelvin. Okay. That's a positive delta S, which means it favors a spontaneous reaction. Okay. Once again, since I'm going to have to plug this into Gibbs free energy, I'll go ahead and convert that to kilojoules, which means I'll divide by 1,000 and get it into 0.1590 kilojoules per Kelvin. We're going to take these values and plug it into my equation. Delta G subscript T, which in this case is 25 degrees C, equal to delta H minus T delta S. Since we're talking about 25 degrees C, that's low temperature, which one of these two processes is going to rule? Is it going to be enthalpy or entropy? Well, since I'm at 25 degrees C, which is low temperature, we're saying that our delta H is going to rule. Since it's favoring a non-spontaneous reaction, then we should see a delta G that has a positive number. Okay, so if we plug in our numbers, we get delta G 25 degrees C is equal to 178.3 kilojoules minus 298 Kelvin times 0.1590 kilojoules per mole. My Kelvins cancel. Add it up, I get 130.9 kilojoules. Since it's a positive number, that's a non-spontaneous reaction, which is what we said is what should happen at low temperature. Okay, so this is no different than we did a problem just like this a few minutes ago. Okay, exactly the same. The major difference is that we have this subscript 25 degrees C down there, and that's your major difference. Now, we want to take this same reaction. I want to crank up the temperature now up to 1,000 degrees C. Now, what are we going to do different in the calculation? Well, we're saying that we're still going to do it at relative 25 degrees thermodynamic state, okay, which means that we're still going to do it at 25 degrees C for delta H and delta S, okay? So nothing's going to change here except for the point that we're going to plug in 1,000 degrees Celsius instead of 25 degrees Celsius, okay? So it's going to look exactly the same. Change the subscript, delta G will be 1,000 degrees C. Plug in our 1,000 degrees C in Kelvin terms, okay, into our calculation and calculate it. Let's see what happens when we do that. Okay, so we're going to find delta G for the following reaction at 1,000 degrees C. So we will use our 1,000 degrees C, which is 1273 Kelvin. We will use our delta H and our delta S as the 25 degrees because we say it doesn't change very much. So we plug that right into our Gibbs free energy equation, just like we did before. Okay, so now I have delta G naught at 1,000 degrees C, so this is one change. I got 1,000 degrees C at the bottom there. My delta HF is 178.3 kilojoules, the same delta H I used at 25 degrees C. Minus, now I'm at 25, I'm at 1,000 degrees C, so I put in my Kelvin temperature as 1273 Kelvin. Time 0.1590 kilojoules per Kelvin. This is the same delta S we used at 25 degrees C. My kelvins cancel, so now I have kilojoules minus kilojoules, and since we're at high temperature, okay, we're at high temperature, we say then that delta S is going to rule, okay, and in our process we said that since it's a positive delta S, it's going to favor a spontaneous reaction, so then we should end up with a negative delta G. Should be a negative number. Okay, let's see what happens. We end up with a negative 24.1 kilojoules. So at low temperature, 25 degrees C, enthalpy ruled, which is favoring a non-spontaneous reaction. So we got a positive delta G. At 1,000 degrees C, the entropy was ruling, which favored a spontaneous reaction, which should be a negative delta G, is what we got. Okay, so we got a spontaneous reaction at 1,000 degrees C. So somewhere between 25 degrees C and 1,000 degrees C, we switched from a non-spontaneous reaction to a spontaneous reaction. Is there any way that we can determine where that switch occurred, what temperature that occurred? That goes back to what we said about delta G is equal to 0. Okay, we see that somewhere this reaction changed from non-spontaneous to spontaneous somewhere between 25 degrees C and 1,000 degrees C. How can we determine at what temperature this switch occurred? Well, basically going to delta G is equal to 0 at equilibrium. Okay, so that's our switching point of where it went. So if we can calculate that, we can figure out what temperature it's going to occur. Since my delta G is a negative 24 at 1,000 degrees C, which is closer to 0 than 130, that temperature obviously has to be somewhere closer to 1,000 than it is to 25 degrees C. Okay, so let's see how close it is to that value. Let's see if we can calculate that value. So to determine the minimal temperature for spontaneity, we can set delta G is equal to 0 and solve for T. So going back to your equation, delta G is equal to 0 equal to delta H minus T delta S. I'll bring over my T delta S by adding it to both sides, which gets me delta H is equal to T delta S. Now divide by delta S on both sides, which tells me temperature is equal to delta H over delta S. That is the temperature at which we're switching from spontaneous to non-spontaneous or vice versa. In this particular case, we're going from non-spontaneous to spontaneous. So if I do the math, I have 178.3 kilojoules divided by 0.1590 kilojoules per Kelvin. My kilojoules cancel, so I have Kelvin in the denominator, which is the numerator, which gets me 1121 Kelvin. Now, since this problem was written in Celsius, let's convert that to Celsius by subtracting 273.15, which tells me that the temperature that this is going to occur, this switch, is going to be at 848 degrees C. That is the temperature that we're going from non-spontaneous to spontaneous. So what does that mean? Let's look at this a little carefully. Basically, we're saying that calcium carbonate decomposes into calcium oxide and carbon dioxide. If we're less than 848 degrees C, it's a non-spontaneous reaction. That means that calcium carbonate is extremely stable at room temperature and above, okay, till we get to that point. So calcium carbonate is a very stable compound all the way up till I get to 848 degrees C. Once I reach that temperature, there's enough energy then that it's going to start decomposing. Okay, at that point, my entropy, changing from a solid to a solid and gas in this case, okay, is enough that it can overcome that stability of that calcium carbonate and cause it to decompose. Okay. So when temperature is greater than 848 degrees C, it will spontaneously decompose into carbon dioxide and carbon dioxide. This is the same way we can calculate the normal boiling point of a liquid. Okay, we're talking about, going from a liquid to a gas. Okay, so if I know the delta HF of the gas and delta HF of the liquid, okay, I can figure out my delta H change. I can do the same thing for entropy, have those values, plug that into my equation here, my delta H divided by delta S, and I find out the temperature that species will boil. I can do the same thing for melting point. Okay, if I'm going from a solid to a liquid, the melting point of something. If I know the delta HFs of the liquid and the solid and the entropies of the liquid and solid, do my law of summations, compare the two, I can get the temperature at which that species melts. Homework. We got homework 48, which deals with calculations dealing with Gibbs free energy.